Welcome to my presentation, Employing Mobile Sensor Density to Approximate State Feedback Kernels and Starting Out with Feedback Control PDs. Michael Dimitriou, WPI in the Aerospace Engineering Department, and this work has been supported through NSF grant. So let me go over the summary, give you an overview of the problem, which is basically the basic idea of this work, formulate the problem, summarize the results, give you some numeric example on applying this approach, and then the conclusions. So we're going to consider three-dimensional systems with time-varying input operator. And of course, the associated state feedback operator is going to be time-varying, especially if you use LQR control design. And since the state X is not available, at each time I want to approximate the full state controller. K is the feedback operator, and X is the state. But I want to approximate this, which cannot be realized because X is not available, by what are some of output measurements. Basically, this summation here, Y are the measurements, and gamma sub I are the gains. So it's equivalent to approximating the time-varying kernel by what is sum of pointwise measurements. If you look at the 1D case, that's essentially what you have, where the control signal is given by the L2 unit product of the kernel and the state. You don't have access to this, but you've approximated by this expression, and since you approximate that at each time t, that means you're going to end up with time-varying gains and also time-varying sensor locations. So as I mentioned, you propagate that forward in time, it will make the sensors to move, and these are the sensors that give you the pointwise measurements. The first question that arises is how to partition the feedback kernel at each time. And the other question is how to move the pointwise sensors at each time. So I'm going to answer these two questions. So let's look at the PD or the process as an evolution equation in a Hilbert space. X dot equals X plus B of T U of T. So explicitly write down the dependence on the input operator on time. I'm going to use LQR to design a controller which cannot be implemented because it requires X, which is the state, and is not available. The feedback gain is given by this expression, where P solves the operator differential Riccati equation, given by this expression here. Since you don't have access to the full state, you need to realize this via an approximation, and this is the approximation I want to use. I want to approximate this by this one here. Y sub I are the sensor measurements given by this expression here. C is the spatial distribution of the sensing devices. X sub I are the sensor locations. So actually, this inner product gives you basically a scalar quantity, which is the ith sensor measurement. So this is the sensor spatial distribution and depends on the spatial variable C and the time varying centroid or the sensor location. In the 1D case, this product of the input operator and the state is given by this L2 inner product of the kernel and the state. K of T and C is the kernel. And again, I would like to approximate this, which requires full state, by this, which only requires access to NS measurements. Okay. Question is, once you have this feedback kernel at each time t, how do you partition it into these n sub s cells? So if I assume that the spatial distribution of the sensing devices for the 1D case is given by delta functions, then this simplifies to this. Essentially, I want to approximate this by this one here. These are the states evaluate the sensor location. And the sensor location X sub I is time varying. That means you can have mobile sensors, and these are the time varying starting output feedback gains. So I need to come up with this partitioning or decomposition of the kernel at each time. And here's how you do that. You want to partition or divide the spatial domain into n sub s cells, I sub I, so that at each cell, the area of the feedback kernel satisfies this. The area of the kernel for each cell is 1 over S times the total area of the kernel. The total area is denoted by A. So each of those cells have the property that they have the same area under the kernel. Once I have these cells, I can put a sensor in each of those cells. I can put it anywhere, or I can apply this procedure and basically decompose or partition each cell into 2 subcells, with the problem that the area of the kernel in each of those 2 subcells is half of the area under the cell. Now, for the 1D case, you have a graphical method to do that. You plot the normalized feedback kernel for a given time, and this is special variable C, and the special domain is 0, 1. So the blue is a normalized kernel. The red is a normalized area function of the kernel. Of course, it's equal to 1 when you go to the end. And to find the cells, you go to the abscissa and decompose it into n sub s parts. So if I let's say I want 8 of those, I'm going to go to 8, 1 over 8, which is 0.125. And where that intersects the red line, that's the first cell here. I would do that all the way up to 7 over 8, and this point here. So I come down, and this point is where is the last cell. So it means that this area here under this cell, all this here, is 1 over 8 times the area under the blue curve, which is the normalized kernel. Now, I need to put a sensor, which are denoted by these black circles, in each of those cells. I can actually decompose or partition each of those cells into 2 subcells. And if I look at their area of this cell, subcell, and then the area under this cell here, they have the same area. It's half of the area in this cell. And that's where I put the sensor. I'll repeat that for the other cells. So to find out the feedback gains, I assume that the kernel admits an expansion. That's a final dimensional representation. These are the projections or the weights or the coefficient of the expansion, and I'm going to use this in this approximation, and that simplifies further. And I replace the x by the test functions. I also assume that x can be approximated or expanded by using this, or since this has to be valid for all x, then I'm going to use a test function phi sub m. And this should be valid for all test functions. When I validate that for all of them, I end up with a linear system given by this expression. Mk equals phi, which depends on the sensor locations, times gamma. I can solve for gamma, we're using least squares estimation, and that will give me this expression here. M is the mass matrix, is the inner product of the test functions. Kappa is the vector of the coefficients of the kernel, and gamma is the vector of the static gains in the expansion here. And the regression matrix basically is the test functions evaluate the kernel location of the sensitive devices. As an alternate sensor guidance, you're going to view the kernel as a sensor density. This is governed by the advection PDE, given by this expression here, and is equated with the derivation boundary conditions and the initial sensor density given by rho sub 0 of C. The question is how to come up with this velocity, which is the velocity for this density. We can use the feedback kernel as the sensor density, modulo constant, of course, and so for the velocity here, because if rho equal to the kernel k, the only unknown is the velocity v. We use the same modified centroidal Voronoi tessellation partitioning to obtain the individual sensor velocities by applying it to this computed velocity v. And then implement after the initial time, because the initial kernel will serve as the initial density, and that essentially will give you the initial positioning of the sensors at time t equals 0. Now for the numerical results, all the details are in the proceedings paper. I'd like to point out that we use 12.1 sensors that are mobile. So this is the evolution or the motion of the 0.1 sensors. So this is the space and this is the time. And you notice that there is no issue of collision avoidance schemes, because each sensor position at a given time is provided by this kernel partitioning. Now, Comparing the performance using a full state, this is the L2 norm, full state versus the static output measure feedback using mobile sensors is not as good as the one with a full state, but the difference is that this requires access to full state. This only requires 12 point wise sensor measurements. Now we use combinational geometry, modified central Voronoi tessellations to partition a time varying feedback kernel that is associated with a full state feedback. And this time variation was induced because of the time variation of the input operator. The approximate full state feedback was done so by a weighted sum of mobile point-wise measurements, and the time varying kernel produced equivalent sensor density as an alternate way of guiding these mobile sensors, and uses a separate advection PD to define the motion of the sensor density. So the first approach provides the position of the mobile sensors at each time, whereas this one that uses this density provides the velocity of each of those sensors. We have demonstrated that on 1D diffusion PD, and as ongoing research, you're going to consider the real-time implementability of this time-varying kernel partitioning. With that, I arrive at the end of my presentation. I'd like to thank you for your attention, and I'm happy to answer your questions.